Hey everyone, welcome back to my Calculus 1 series. In today's lesson we're going to be going over LHospitals Rule and indeterminate forms. So to start off, we're going to go over what an indeterminate form is. And essentially, if we're asked to find the limit of like two functions, a lot of the times we can get something where we have, like if we're going to plug in the a value into f of a, we might get something like 0 over 0, or we can get like plus minus infinity over plus minus infinity, right? And then these forms look kind of like weird and we don't really know like what to do here, right? This will cause like a division by zero error, and then here like this is like a mess. So these are called indeterminate forms. Now there will be a couple other indeterminate forms that we'll go over, but these are the two basic ones where you have 0 over 0, or you would have like infinity over infinity, right? So before, if we had a limit like x approaches infinity of x squared minus 1 over, let's say, 2x squared plus 1, right? And we were trying to find the limit at infinity of it, we would factor out the highest power, in this case x squared, to get something in the form of like c over x to the n, right? And then we could use the property that c over infinity would equal to 0. And then we could simplify that and then kind of work through it. But the problem is that there's a lot of functions where we don't have this common factor of x squared on like both the numerator and the denominator. So how would we go about solving that? An example of this would be like if we have the limit as x approaches 1 of ln x over x, how do we solve this, right? If we plug in 1 into here and plug in 1 into here, or sorry, this would be x minus 1. If we were to plug in x equals 1, we would get 0 over 0, right? So like, again, this is indeterminate form. So what are we to do about this? And likewise, like we can say the same thing about the limit at infinity. So if we were to have the limit of this function at infinity, we would still get infinity over infinity. And like there's not much we can do at these forms. So this is what LHospitals Rule is going to try and solve for us. And we're going to start off by writing down the definition and then kind of going over it. So here's LHospitals Rule, and let's go through the definition first. So we suppose that there are these two functions f and g and that they're differentiable. Obviously g prime at x is not equal to 0. We'll see why later. It's because of this definition right here, but this is important. It's on the open interval and it's containing this value of a, and it's because we're approaching this value of a. So we want that the value to be within the interval that we're talking about. And then we say that if the limit as x approaches a of f of x and g of x is both equal to 0, meaning that we would get, if we were to take the limit as x approaches a of f of x over g of x, plugging this in, we would get 0 over 0. So this would be an indeterminate form. Or we can have that we would get the limit as x approaches a of f of x, g of x is equal to plus minus infinity over plus minus infinity. So that's all this condition is saying right here, right? We assume that the separate limits are equal to plus minus infinity and plus minus infinity, and then if we were to take the like the division of the two functions, then we would get an indeterminate form, which is right here. But LHospitals says that if we have these indeterminate forms, what we can do is we can evaluate that limit slightly differently. So instead of just taking the limit of f of x over g of x, what we can do is take the derivative of f of x and then divide that by the derivative of g of x, essentially differentiating both the numerator and denominator. And now you can see why this condition right here was important, that g prime of x was not equal to 0, because otherwise we would get a division by 0 error right here, and we don't want that. And it's important to note that also LHospitals Rule works for one-sided limits and limits at infinity. So now let's use LHospitals Rule to solve the limit that I was previously giving right here. And let's figure out how we can solve it. Before we couldn't because we get an indeterminate form, but now that we know LHospitals Rule, let's apply it and see how we would go about solving this limit. So again, we can't plug in this value of 1 because we would get something like ln of 1 over x minus 1. In this case, it would be 1 minus 1, which is going to be 0 over 0. So we cannot do this. But what we can do instead is apply LHospitals rule, because we notice that we get it in the form of 0 over 0, which is an indeterminate form. Let's use LHospitals rule. And if you remember from the definition, LHospitals rule says that all we need to do is differentiate the top and the bottom, so the numerator and the denominator, and take the limit of that. So let's go ahead and do that right now. So I'm going to keep the same limit as x approaches 1. And now we're going to take the derivative. So I'm going to call this f of x right here, and this we'll call it g of x, just to like stick alongside the definition. So the f prime of x would be, in this case, it would be d over dx of ln x, and we know that this would be 1 over x. And then g prime x would be d over dx of x minus 1, which is just 1. So we would end up getting, right, this would be f prime of x and then g prime of x. So we would end up getting the limit as x approaches 1 of 1 over x over 1. And now we can go on to simplify this by saying that it's just the limit, so x approaches 1 of 1 over x. And now the limit is pretty easy to solve. We're now able to plug in this 1 basically because there's no error plugging it in. This function is continuous on 1. So we can just plug it in and we would get that the limit of 1 over x is equal to 1 as x approaches 1. So there you go. This is how we would go about solving this limit using L'Hopital's rule. So when I started off talking about indeterminate forms, I also mentioned that there's going to be a couple more forms apart from just the regular 0 over 0 and then plus minus infinity over plus minus infinity. There were going to be a couple of other weird ones that we would want to convert to these forms so that we can use L'Hopital's rule. So now we're going to talk about indeterminate products, and it is what it sounds like. It's when we don't necessarily have a division of these weird inputs, but we would have a multiplication of them. So it'd be in the form of like 0 times like plus minus infinity. And this right here, it's indeterminate because we don't know what like term like kind of trumps the other or like wins essentially. Like if we were to take the 0th term as like greater than or like the winning term in a sense, then we would get that this equation evaluates to 0. But then if we were to take infinity as like the winning term, then we would get that this equation equals to infinity, which like that's why these forms are called indeterminate, because we don't really know which term we assume is kind of like the greater one or like the winning one. So we can write, if we let's say have f and g, right? If f and g are in the form of like this indeterminate stuff right here, if it's in the form of this, we can kind of rewrite it to get it into this format so we can use L'Hopital's rule again. We can write f of g as either f and then 1 over g, or we can write it as like f of g is g and 1 over f. Essentially all we want to do is we just want to take the reciprocal of one of the functions and then throw it in the denominator, because this format right here is like both these formats are equivalent to saying like this. That's why there's that equal sign there. They're completely equivalent. It's just now this would resemble this format right here, and we would be able to use L'Hopital's rule. So let's go through an example of how we could apply this. So let's say we were asked to find the limit as x approaches 0 from the right side of this function x ln x. So I'm going to refer to this as f of x and then this as g of x, just to stay like close to this definition right here. So again, we can't just plug in 0 because we're going to get 0 times negative infinity in this case, and this is an indeterminate form. So we don't know how to solve this, but now we do with L'Hopital's rule. So what we're going to do is we're going to write it in this format right here, where we take g of x and then we throw the reciprocal of 1 over f in the denominator. So if we go ahead and write that, this is going to be limit as x equals 0 from the right, and then we're going to keep ln x at the top, and then take the reciprocal of f of x, which is 1 over x. And now we have this indeterminate form again, because we're going to have minus infinity over, well, this would give us a division by 0 error, but we can kind of say it's infinity in this case because it's coming from the right. So we would have this indeterminate form here, and then we would try now to use LHospitals Rule. And again, LHospitals Rule just says to differentiate the numerator and the denominator. So I'm going to go ahead and do that right now. So there we go. We have differentiated both the numerator and the denominator. Now all that's left to do is to simplify this. So we could say that the limit as x approaches 0 from the right, if we go on to simplify this fraction right here, we would end up with minus x. And now we know we can just plug in 0, and we would end up getting 0. So now this limit is equal to 0, and we're able to successfully solve it using the indeterminate product in conjunction with LHospitals Rule. So now let's talk about indeterminate differences. And just like indeterminate products, indeterminate differences is when we can't figure out which term wins, because they're both kind of like conflicting. So in this case, we would have something like the limit as x approaches a of f of x minus g of x. And in this case, both of them would evaluate to infinity. So you'd have something like infinity minus infinity. And again, we're going to try to convert this to the regular format that we see, which is 0 over 0, or plus minus infinity over plus minus infinity. So let's say we have this problem right here where we have the limit as x approaches infinity of e to the power of x minus x. And we can see that this is the indeterminate differences because e to the power of infinity is equal to infinity, and we would end up getting infinity minus infinity. So one of the ways that we can go about solving this problem is by factoring out either one of these terms. I'm just going to choose to factor out e to the x because it's just the leftmost one. But the solution would be the same, factoring out the other term too. So let's go ahead and factor out e to the x. We would end up getting 1 minus x over e to the x. So now we can simplify this limit by taking the product of these two functions right here. So we could say that this is the limit as x approaches infinity of e to the x times the limit as x approaches infinity of 1 minus x over e to the x. And we know what this limit right here will be. It will be infinity because we can just plug in infinity to the x, and then we would end up getting e to the infinity, which is just infinitely large, so it would be infinity. So we'd get infinity times the limit as x approaches infinity of 1 minus x over e to the x. And we can simplify this limit even further by splitting it up by taking the limit first of this and then the limit of that. So I'm going to go ahead and write that. So there we go. Now I'm going to simplify this limit right here because it's pretty obvious what this will be. That limit will just equal to 1. So we're going to get infinity times 1 minus this limit. Now, we can see that this right here is indeterminate form because it is in the form of infinity over infinity. So we're going to use LHospitals Rule right now to simplify that. And if you remember, all it says is to take the derivative of the top and to take the derivative of the bottom. So I'm going to continue on with it down here. We're going to get infinity times 1 minus the limit as x approaches infinity. The derivative of x is just going to be 1, and the derivative of e to the x is just going to be e to the x. And now we can see that we no longer have indeterminate form because we're going to have something in the form of 1 over infinity, and we know that this right here is equal to 0. So this limit right here is going to equal 0. So essentially we're going to get infinity times 1 minus 0, which is equal to infinity times 1, and then this is equal to infinity. Sorry, I shouldn't be putting these arrows. It should actually be an equal sign. We have solved the limit using LHospitals Rule and the indeterminate differences. So now on to the last section. It is indeterminate powers, and it's when we're taking the limit of a function that is to the power of another function. And there's a couple more scenarios for this one, so I'm just going to go ahead and quickly write those out, and then we're going to go over them. So here they are. There are three conditions basically, and the first one is when we have the bottom function right here, the base sort of, being equal to 0 and the power equal to 0. So we would get something in the form of 0 to the power of 0. And this is indeterminate because like anything to the power of 0, like x to the power of 0 is equal to 1, but if we have a base of 0, that to the power of anything is equal to 0. So again, we kind of don't know which one to use. Then the other case is that we have the base being equal to infinity, which is this right here, and then the power is going to equal to 0. So we get something in the form of this. And again, for a similar reason to this is indeterminate. Lastly, the final one is when we have a base of 1 and a power of infinity. This would be the last form for indeterminate powers. And there are two ways that we can go about solving these and kind of converting them to LHospitals rule. The first way, we can take the natural logarithm. So let's say we have the function f of x to the power of g of x, right? We could go about solving this by saying, okay, let's take the ln of both sides, and then we would end up getting this. If you remember the rule, like on the right side, we would get ln of f of x times, to the power of g of x, but ln rules state that we can drop before. That's why I have it in front right here. Now, we can do that, or the second method is that we can write this function as an exponential. And the way we can do that is we can kind of just elaborate on this right here. So let's say we had that. We're just going to take it one step further and basically raise both sides to the power of e. So we'd get e ln y, and then we would get e to the power of gx ln f of x. However, we can simplify the left side and say that this right here would be y is equal to e gx ln f of x, because these two right here are inverse, like e to the power of something and ln to the power, the ln of that are inverses of each other. So they would cancel, and essentially we would just get back with the input variable, which is x. And so let's see how we can apply this. Let's say we have the limit as x approaches 0. Let's do from the right, of x to the x, right? Again, this is indeterminate because if we plug in 0, we're going to get x to the 0, which is apparently always equal to 1, but we're also going to get that 0 to the x, and this should always be equal to 0. So again, we don't know which case to kind of take, so this is why it's indeterminate. Now, I'm going to use the exponential version of it. I'm going to do step number 2 because step number 1, like, you can use it, but you're just going to end up doing like step number 2 somewhere down the road after, because you're going to want to simplify for y. So I personally like step number 2, sure, not step number 2, but method number 2 a little better. So I'm going to do that right from the beginning. So we have the function y is equal to x to the x, right? So let's go ahead, let's take the ln of both sides, and this is going to equal to x ln x. And now let's raise both sides to the power of. So there we go, we have successfully done that. And now let's apply the limit to this. So because e is a continuous function, we can kind of use the limit chain rule, and we can sort of take the limit of only this function right here. So it would look something like e to the limit as x approaches 0 from the right of x ln of x. And now if we go back up in the examples, we have already solved this. It's right here. We have already solved this right here, and we figured out that it's equal to 0 using LHospitals rule. So I'm not going to go ahead and solve this. but you can refer back in the video. There is the solution for this limit right here, but it's going to equal to 0. So we're going to get that this is going to be e to the 0, which is equal to 1. Sorry, I don't know why I keep writing these arrows, but the whole limit is going to equal to 1. And again, we know that this right here is going to be solved through LHospitals Rule because it is the product. It's an indeterminate product. So we're going to use LHospitals Rule to find this limit, and then we're going to raise e to whatever that limit was. So that's how we can apply the Indeterminate Powers and LHospitals Rule together to find out the limits of some of the more complex functions. So that's it for today's video. We've covered LHospitals Rule, and it's really good at helping us figure out limits of more complex functions that perhaps have like nothing in common to factor out or like simplify. We would use LHospitals Rule a lot of the times to figure them out. I hope you enjoyed the video. If it's helped you out at all, please like and comment as to what it helped you out with. Like usual, if you're new to the channel, please like, comment, and subscribe. It's greatly appreciated. And yeah, I will catch you guys in another video.